Hello, everybody. Welcome back to another episode of the Flocode Podcast. Today, I'm going to be speaking with Liam Brannigan, a fellow Irishman and a data scientist. So, Liam's going to be helping us take a bird's eye view of the data science landscape, and he has quite a diverse experience across many different domains, from finance and oceanography to renewable energy and now data engineering. So he can understand where these tools fit into stuff like an engineering workflow, which is what we'll explore in the episode. I first encountered Liam's work through his excellent Udemy course on polars, which is a really, really good introduction. It's succinct, it's concise, and I highly recommend it. It's what I used. And while I do still use Pandas for a lot of data science applications in my work, I'm starting to use polars more and more as the data sets become larger and higher fidelity. So I had a great time chatting with Liam, and we could talk about this stuff for a very long time. So if anyone has any questions, hit me up down below. As always, thank you very much for the support. I'll see you guys in the next one. Bye-bye. Hello, everybody. Welcome back to another episode of the Flocode Engineering Insights Podcast. Today, I'm very pleased to welcome Mr. Liam Brannigan on the podcast. He is a fellow Irishman. Welcome aboard, Liam. Nice to have you.
Yeah, thanks, James. Nice to be on.
So, Liam has a lot of experience in the field of data science, and we'll talk about that in one moment. But the overall objective of this particular episode is to give a sort of a bird's eye view of the data science landscape and to try and explore how and why it might be of use to practicing engineers. So, Liam, as is tradition, you must first explain what your life philosophy is in a nutshell.
Yeah, well, it's good because I've been thinking about my career in the kind of lead up to this, and I realized that if you look back on it, that I guess a lot of my life philosophy is about really following your interests. So at certain points in my career, I've made some just big changes, and those big changes have happened because I found what I was doing, wasn't interested, got bored, saw something else that I really want to work on, and it wasn't about hanging around and saying, oh, will I, won't I? And most of those cases, few days, talk to friends and family, talk to people I trust, and then go for it and kind of be brave and just be ready to follow and be excited about what you're doing.
The psychology of making a big change is fascinating. And it's like, it's human nature, I think, to just think initially you're like, no, what if this happens? What if that happens? What if and you're in a doomsday, and at least for me, I'm in like a doomsday swan dive.
Mm-hmm.
And then, but every time I've taken some sort of leap, it's worked out very well.
Yeah, and actually the biggest penalty whenever I've done these kind of career changes, it's not being like changes in money and things like that. It's always been the drop in status from being where you're someone who knows something and you move to a new domain and suddenly you're the coolest person and you just got to spend 6 months a year kind of paying your dues, getting back up to speed again. But it really pays off when you're excited and you're interested in what you're doing, then you just learn so much faster of what you're up to.
So give us the rundown of all of the different leaps between domains that you've done throughout your career, because there are many and they all kind of facilitate and help one another.
Sure, and I'll kind of tie that back in because a lot of it comes back to my experience with coding and experience with Python. So I started off with a maths degree. I did an undergrad in really pure mathematics in Edinburgh University, and then followed a kind of natural path from there into an actuarial consultancy. So and there was advising on pension schemes, so working in London, kind of in the city, kind of talking to big investors and things like that. However, it was actually kind of boring. It's a really interesting problem, this idea of how you actually build these investment portfolios. But it was like late like 2006, 2007, the coding revolution, where it's becoming not just a thing for people working with hardware and stuff like that, but actually the data science stuff was emerging. But we were a room full of people with like maths degrees from Oxford and Cambridge, but everyone was just using very basic Excel functions. And I was like kind of seeing this revolution happening outside and thought, it's just not happening here. And at some point also, after a few years, this consultancy, you weren't really kind of doing quantitative modeling. And I felt that's what I should be doing. Got kind of bored of a few cycles of writing the same reports over and over. And then I found a book on oceanography written by a marine biologist talking about how the wind drives the ocean, how the tides work, all this kind of stuff. And I thought, oh, this is fascinating. I read it for like 2 weeks and then went for a holiday. When I came back from the holiday, I was like, I got to do this. So a few days later, talked to my friends and family, as I said, and then quit that job and went to do a master's in oceanography. And that was in Bangor University. It was a great experience because that was the start of me actually learning to code. So at that stage, everyone in oceanography and climate science was working in MATLAB. So we learned to code in MATLAB and started kind of getting up and running. And from there, I went on to do a PhD in Oxford, again in the physics department, but working on oceanography. And again, it was still MATLAB. And one of the kind of experiences now that I think a lot of people wouldn't believe if they come into the Python data science world today was how much you were on your own. Like you had MATLAB, say, but then now if you want to use like some engineering package, you do like pip, you install that package and you've got a bunch of functionality. That didn't exist like back in 2010, 2011, that even when you had Python, or even especially in MATLAB, that if you needed someone else's code, if you were lucky, maybe they posted it on their website, or you knew a postdoc who like could email you a bunch of stuff that didn't work and had no documentation. And then Python started taking off. There was this transition away from MATLAB because of the licenses and the lockdown, and it was got really tied into using university computers. You couldn't just move between jobs. It was all kind of a lot of friction there. So then this kind of Python revolution started happening in in climate science, in the data science world as well. Around 2011, 2012, machine learning was starting to become people talked about. And so some the kind of the hipsters in like among the PhD students, they started using Python and started really evangelizing. So I got in on that. And then the first thing that like just blew my mind coming from MATLAB was that suddenly you weren't working on your own anymore. There were all these community open source projects that were on GitHub that you could really install, and just like you weren't like there's a major package in Python called Pandas that almost everyone will kind of come across for working with CSV, spreadsheet, tabular data. A friend of mine put it at the time that we all spent our PhDs around 2010, 2011 building really bad versions of Pandas by ourselves, like thousands of PhDs across the world. And then we switched to Python and suddenly it's like, oh, okay, everyone just worked together to make one amazing package instead of like literally thousands of people all writing the same terrible code to do like the same problems of loading CSVs and transforming them into group by and all this kind of stuff. So that was going from oceanography into that was going from finance into oceanography, which is a bit of a shock and took a few years to kind of build back up there. So then I did my PhD, all in MATLAB actually. But then by the time I moved to my postdoc, that you kind of the clean break at that point. So I switched to Python. And I didn't just kind of start using Python, but I also got into Twitter and data science Twitter. And that really opened my eyes to not just what was happening in climate science, but the fact there was all these really exciting things happening and you could really keep up to date and learn lots of new stuff from social media. So for me, social media has been really important because I've never really worked many places where there's people around me who can say, oh, this is the hot new thing. It's always been a bit that exciting process of like going on Twitter every day and seeing like, okay, what's the new packages? Where's the hype? What's gonna revolutionize things? What's just a kind of a fairy that'll be gone in a few minutes? And so I guess in my postdoc, at first I was using Python just to do my analysis, but towards the end, as I got better at it, it was more about not just running a script and doing a bit of analysis, but actually building systems. So I guess like writing scripts to run scripts and build more of an end-to-end process, what I call now like a data engineering pipeline, basically. There's a lot of similarities there between climate science and with kind of regular engineering. That when I was a modeler in climate science, and what you're doing for a lot of the time is actually you're working with these climate models. And if people maybe have never thought about what a climate model is in detail, but basically it's a massive set of partial differential equations that have been written out as just numerical equations, and you're integrating that forward in time, and that simulates the fluid dynamics. So I'm sure it's actually quite similar to a lot of classical engineering problems. But then you've got to feed all the data into that model, and then it generates huge amounts of data coming out of it. So you can't just be sitting there kind of cranking the handle so that every time you want to run 100 experiments, eventually you realize that the important bit isn't just a script to analyze the output of the experiments. It's a script to actually run the 100 experiments, and then it's a script that can process the outputs of the 100 experiments at once and actually give you all that in a feasible way. And you just learn how to keep on just scaling up and up and up and handle bigger and more exciting problems.
It's like it's fractal. The early days where you would do one partial differential equation way back, and you would have to be like, okay, this is the situation that we're going to assess. And does everybody agree? Because this is going to take 2 weeks. So everybody has to agree. And then, like you say, over time, there's like another layer of extrapolation, and then another layer, and then another layer. And then suddenly you've got these giant climate models that are essentially, 20-dimensional CFD models with God knows how many inputs and outputs. So yeah, fascinating. Sorry, just a thought there. Continue.
Yeah. So then, as I was going through that, I was then a postdoc in Stockholm at Stockholm University, again in oceanography, and at that stage, I was really starting to do work. Whereas during my PhD, if I'd wanted to run 100 experiments with my model, that would have been taken like 3 or 4 months. But by the end of the postdoc, that was something I could crank through in a week, basically. And the main limiting factor was just the supercomputer at that point of actually getting all your jobs into the queue. However, at that point, I was also going to meetups and I was engaging a lot more in data science Twitter. And I was kind of seeing just how tough it is to actually make a career as an academic in terms of job stability and having to move around a lot and short contracts and then the workload and so on. And then I met people doing commercial data science, and I was thinking, these people actually seem a bit less stressed than the people I know who are academic faculty. And so I decided to make the jump into commercial data science. However, I did it with a view also that I was working on a certain branch of oceanography, and I was thinking, we got a bunch of these climate problems, and I feel like if I solve this equation from like 4th order to 6th order, that's not really going to move us forward in terms of addressing climate and environmental issues. A lot of the really important stuff is happening in business, in industry, in terms of actually building out the solutions that we need for climate and environmental problems. So we need to be there as well. So I was kind of really happy to make that move out of academia and go into the commercial world. So I went into a company called Analytics Engines, which was a kind of like analytics consultancy in Belfast. And I was really lucky there to work with some really top class software engineers. And so I'd been lucky in my PhD in Oxford, obviously. I was there having coffee with people who are like Nobel Prize winners who were writing the IPCC reports. So having a really good background there. But then working with these guys who were top software engineers just gave me a whole bunch of other skills of actually, okay, how do you actually build robust software that doesn't just fail like a classic scientist script will run once and you write the paper and you don't really care if it works again a week later. As a software engineer, you want it to work today, you want it to work tomorrow, you want it to work in 3 years' time if nothing happens. And also things like starting to learn how to test code, how to run things on the cloud, how to like deploy things in the cloud. That was all like a new set of skills I got in that job. Then I went into a bit of a period of contracting and freelancing because I felt I was learning lots of skills. But when you're working for a consultancy, as you maybe yourself, you don't always have control over what projects you work on. It tends to be whatever comes through the door, that's what you got to jump into. And I was lucky I worked in projects like text analytics and geospatial and pharma analysis, a new thing every month almost. But then I wanted to go freelance. So partly I wanted to set up more of a training business because I felt I've always enjoyed teaching. I did tutoring for the physics undergrads in Oxford, really enjoyed that. And I felt I wanted to do some online training and share my knowledge of Python because I was kind of accumulating quite a lot. So I took some time off to then write the Polars course. And I'll talk more about Polars later. But yeah, I sort of made a course, put it online. But I always didn't want to be just doing online training. I want to have the synergy of actually being a day-to-day, like at the cutting edge, deploying models, building it, and also working on those climate problems. And that's when I got a big break. I was approached by a company, again, based here in Belfast, called Julian, and they're building battery optimization software. And so that's my current job. I lead the data science team there. And the idea is that you now have a lot of households that have solar panels, and then you get a battery so that you can store the energy when you're out at work during the day and then use it in the evenings. You can also buy energy cheaply overnight from the grid and then use it during the day when it's expensive. And now increasingly you get big commercial industrial properties, might be a construction site, might be a big engineering site, for example, might be a big factory that they've got all the big energy needs and they want to just get the cheapest energy possible. So they might have a wind turbine and solar panels on site. They might just be buying cheap from the grid, but the battery's there to kind of smooth out all those things and give them more kind of flexibility. And that's great for the kind of energy transition because at the moment here in Ireland or the same in the UK, for example, we've got too much wind power, more than we can use. So we need to be harnessing that, storing it up in batteries, because at the moment we're paying these wind farms just to shut off. So this is a major like blockage basically in our effort to actually decarbonize the economy and actually do it at a good price that like will generate growth and generate jobs and interesting jobs and good jobs as well.
Very cool. That's you covered a lot of ground there, and yeah, I mean, I'm in the energy sector myself, so we're always looking at ways to incorporate batteries to intermittent power, more of a at more of a utility scale than what you're talking about. But that's a great background, diverse. You've touched on many different industries, so I think that puts you in a great position to talk about this topic, sort of at a higher level, and just to kind of set the stage for you. Most engineering design consultancies around the world are Excel is still the main workhorse for data. Now, each domain, structural, civil, geotechnical, hydrotechnical, they all have their own commercial software packages where you have certain people in the office are experts in, structural tools or the geotechnical tools. But at the end of the day, the outputs of all these different commercial tools are big packages of data.
Mm-hmm.
And when we work on these large multidisciplinary projects, there's always gaps between the domains and trying to integrate. There's a little bit of massaging of the data. If you've got a big output from geotechnical analysis, you got to mesh that with the structural analysis, and there's a gap there, and it's like, okay, how do we get these two jigsaw pieces to fit?
Mm-hmm.
And in my opinion, this is where data science skills come into play, being able to manage and wield the various domain data types. Mm-hmm. So let's assume that the listener to this episode right now is a practicing engineer. They're comfortable with their commercial tools. They're comfortable with Excel. What is your pitch for the benefits of the basics of data science?
Yeah, it's a good point. So in that list of kind of jobs, one of the jobs I didn't mention was that I did a period of contracting for actually a big kind of engineering firm here. And I was working with either their in-house engineers or their consultant engineers and got to see kind of how they worked. And it was very much like you described with, they had these big spreadsheets basically that were the outputs of models, and they needed to transform them a little bit, maybe join them and then feed them back into another model. And so it was kind of eye-opening for me to see that, because essentially there were a number of big problems. The first was that it took so much time that they had this idea that they had kind of big data sets. They didn't actually have big data sets. It's just that Excel could only handle very small data sets. In terms of your computer, even if you don't have a very impressive computer, it's just some old thing that the work is giving you that is cheap, that's still actually able to process lots of data. But Excel is not able to process that kind of volume of data. So it's kind of interesting that I've heard of people describe, people today who go out mining, not with these huge trucks and machines, but just still going out with shovels and buckets as artisanal miners. And I felt that these like highly qualified engineers were basically artisanal data engineers. That whereas for me, coming along to the same problem, I could write a script in Python and it will process it all just in a matter of seconds. That instead they were spending like days and days to process exactly the same data in the same way, because they were having a bunch of issues. Firstly, they had maybe 5-10 years of data at this point, but because it was so many rows, they didn't fit in Excel anymore. And they were like, we got like 1 million rows here. It just doesn't fit in Excel. Well, like in Python and Polars, for example, 1 million rows is nothing. Like 100 million for your laptop, yeah, you might start to struggle. 1 million shouldn't even be the blink of an eye, but it wasn't just that it was hard. They thought, this is like a major problem we have. So my first job was to take their kind of big spreadsheets that were always falling over and failing, and they couldn't transfer them over the network because they were so big and all these problems, and basically to extract all the formulas and rewrite them as a Python script. And then in that case, I compiled that Python script into a Windows executable so that I could get it on the system and they could run it. And they were just astonished that this job that had taken them all day, that when they ran the executable, it ran basically in seconds. And it really made their computer hum. Like when I got it going, I really put a lot of everything in parallel and stuff like that in it. Like their computer was really burning for those 10 seconds, but then it just like stopped and they thought there was a problem the first time. And then they saw all these files sitting there. So there were a whole bunch of issues with that. Firstly, that it was slow. Secondly, that it's not shareable. That if you've got a bit of functionality in there that like does some kind of regular calculation that you do a few times, that you can't really just email that to someone. You've got to email the entire sheet. That essentially you've got the data, and the code are all kind of integrated there together. So obviously, I should say at this point, Excel is great and does many great things, but it's not a tool for doing this kind of large bulk analysis. And when you get to that point, then you've got a problem in your hand. So it's not searchable. That if someone comes along and says, "Oh, you know that function you wrote last week to calculate the density of whatever kind of tracer they put in the fluid or something," it's just a question of someone going, "Oh yeah, I think that might be in the spreadsheet from like last week," and you've got to go and just open up all the sheets. That whereas for me, if someone comes and asks me a question on my current job, for example, of, "Oh, where is that thing which converts everything from watts to kilowatts?" then I'm like searching, okay, watts to kilowatts, and I've got a huge code base. But in VS Code, I can find that in seconds, and then okay, there it is. And not just me, but someone else coming along can also just find that, and it's searchable, and everything's findable and shareable. The other point was that it was really buggy. And so here's the thing, that because the data didn't all fit into one spreadsheet, so they had to do, if they had 10 years of data, they had to have 10 different spreadsheets. And then you find that after 4 or 5 years that someone realized there was a mistake in the formula and so like fixed it. But the previous 5 years, they still had the mistake in there. So for me, when I was writing it, I was taking out all the formulas, and then I was taking out tiny subsets of the data, just like 1 or 2 rows, and writing what you call like a test script. And so a test script is something where if your data set is, say, 500,000 rows, but you apply the same formula to all of those 500,000 rows, what you do is you just take one of those rows, feed it through the test, and then check that if it passes, then nothing happens. And if it doesn't give the right result that you've kind of calculated manually, basically, then it kind of raises a flag and says, "Hey, stop, you got a problem here." And once I started doing that, I realized that actually there were loads of bugs. And it had all happened because often people had fixed bugs, but then bugs hadn't necessarily been propagated backwards. Or that something would change year to year and they'd know there was something strange, but then you can't actually go and compare all those 10 files. Whereas again, if you've got like Python scripts, it's actually like easier to kind of just take all those and compare what's happening. There was kind of like a bigger issue again around spreadsheets, and it's worth just thinking about data formats for a second, about what is a spreadsheet. And because one of the things that I did there was that I took their kind of spreadsheet workflow, like they receive spreadsheets. There was no choice about that. Often we have to deal with this reality in big organizations. Although we might like to work with, say, CSV, we can't just tell the other team, "Hey, give me CSV," because their pipelines are set up to give you spreadsheets. And so you have to accept that as the input. However, in this case, in order to do the calculations, they needed to do like a series of transformations. First the raw data, then the clean data, then you combine it with something else, then something else. So for me, when they had done that themselves, they basically had, say, 10 columns in the spreadsheet, 500,000 rows, then a couple of cells break, then another 10 columns with the next bit, another 10 columns. Whereas I split that up into, you take the spreadsheet, you do the first bit of code, you write that out to a CSV, then you read that CSV into the next bit, you run the next transformation, write that out to another CSV, break it up into stages as a pipeline. And the advantage of that is that you then have the intermediate results. You can actually see those. And if someone just wants to see the calculation halfway through, they don't have to open up this huge spreadsheet that's got far more data than they need. But there's another issue. It's not just having too many data sets in the same spreadsheet. It's a question of, again, what is a spreadsheet? So an Excel file is basically a zip archive. So you can actually go in and just right click on an Excel file and like unzip and see the actual files that are inside it. It's like it's nothing different from like a regular zip file that you might get from a colleague. And inside there's a bunch of XML files, which is this kind of like thing you might see in a web page if you do like a bad like web address or something like that. It's just kind of like all these square brackets, this kind of format for nested data. And so what's the difference between that and a CSV? And this confuses people because in a spreadsheet, a CSV looks exactly the same as like a spreadsheet. If you open either in Excel, they look the same. However, from the perspective of something like Pandas or something like Polars, if you go to read data from a spreadsheet, so it has to do this first thing, it has to unzip that spreadsheet. That takes time to like decompress all the stuff in it. Then it has to parse all this XML. And the thing about XML is that with Polars or Pandas, you know the data is basically a bunch of like columns of different data. But with XML, you can't kind of take that as read. So you just have to parse the entire thing and actually figure out the structure each time. And XML works for Excel because it's not just data. It might also have like formulas in there. It might also have charts and stuff like that. But if you're just processing the data, what you really want is just all the data, lined up in columns. So this is why it's actually way faster to work with CSVs than spreadsheets, because with a CSV, when Polars or Pandas comes to it, that actually it knows all that data is going to be a bunch of rows. Everything's going to be separated by a column, and it'll all add up to different columns of data. When you come to a spreadsheet, it's got to do this unzipping step to decompress it and get it parse all these XML, which isn't built for fast parsing. So in my Polars course, for example, I have like a section on working with spreadsheets, a section on working on CSVs, a section on working with Parquet files, different things. And when I run my test suite, so for each one of these, I've got a bunch of automatic tests, which tests are the Polars functions working the right way. And it kind of zips through all these different tests. And then it gets to the Excel one, and suddenly it's like bump, bump, bump. It goes so slow, even on these tiny spreadsheets, because there's just so much overhead in processing spreadsheets compared to processing CSVs. So that's one of the first things I'd say. If people are thinking about working with Python and working with Pandas or Polars, that if they can convince their colleagues to actually start working with CSVs, that's actually a kind of a major speed up that they'll get. And it's a much better way of working with that kind of data.
So I guess just to kind of add some color to what you just mentioned, the two data analysis libraries that you mentioned, or packages, Polars and Pandas, are kind of the two leading Python packages for basically any and all types of data manipulation and management. I started off with Pandas and find it tremendously easy to work with. And because of your course now, I'm starting to lean into Polars. So for people out there that are kind of unfamiliar with how these packages work, they're basically a way of, as Liam just described, you can interface with a spreadsheet or with a CSV, and then you can pull all of the data in those files and essentially turn them into objects that can be easily manipulated and managed. And you had mentioned they're taking
more specific tables, I guess we're talking about here. It's not something kind of obscure. It's a big table of data.
A giant table of data, and each row in those, each column in those tables, or series in those tables, can be manipulated and calculated with and just dealt with really easily. So I guess just zooming out, Liam, from a purely a fundamentals perspective, like why is data science a preferred approach? Like, why is this sort of coding based data science a preferred approach in your opinion, rather than being in there with like a shovel using Microsoft Excel?
The major point is that it's just so scalable that when you start working on this tiny data set, that, like, for me, one of the reasons why I love Polars and kind of brought it in for my team is that we might just have one client's worth of data. It might be 10 rows in a CSV, that's fine. But then later on might be 100 million. But we're using the same thing. We don't have one tool for this, and then you got to shift over to that tool for that thing. That actually these tools, like, they span like an enormous kind of range of scales. Like, for almost anyone listening, I'm sure that like almost every problem they have can be solved by this one tool. So it's not the case that you then have to like, oh, I got this one for this problem, and then I have to learn this whole other skill set, this whole other domain for that other problem. You can just have this kind of one thing. I also feel like they're really good at kind of bringing forward these kind of key concepts. So for me, whenever I interview a junior data scientist, there's a few concepts I want them to know. One is group by. So this idea that, let's say your table has got data from 3 different sites, and let's say it's kind of a telemetry of like water flow or something through some pipes. And so you've got a column there, or you've got the first column says the ID of which pipe it belongs to, and the second column is the timestamp, and the third is what the flow is. And then you say, okay, well, I want to know what's the average flow in each of these pipes. So then you do a group by operation. So it gathers all the rows belonging to the first asset together, takes the average of those, all the rows belonging to the second asset, gathers those, all the rows belonging to the third asset, gathers those, does the average for each, and then brings them back together into a single output. That kind of thing in Excel, like, that's one of the fundamental things of data engineering. But yet in Excel, if I was doing that, like, I'm not actually sure what that kind of fundamental idea is. And the other one is joining data sets. Like, I'm sure there's some crazy tortured things out there of how you've got data set A that say, again, this is like the flow data. So you've got your kind of asset ID, you've got your timestamp, you've got your flow record. And then you've got another table which has all the metadata about each asset. It tells you as a day, where it is, when it was installed, what's the model, what's the make, so on, so on. And you want to bring those together to actually compare them. That's a join. And I think if you're using the data frame approach, then you just learn that like on day 3 or day 4, and then you just know, okay, that's how you do that. If you work in Excel, that something, those kind of concepts just aren't really, maybe you might call it atomic. And so people can end up doing some crazy stuff because they're solving these problems which have been solved, but they're just creating these like artisanal solutions to come back and actually get them together.
Yeah, that's exactly right. That's what happens is it's the same fundamental problem, but you give it to you give 10 different engineers the same problem, and in Excel they'll do it in 10 different ways. Whereas if you just stick to the fundamentals of using either pandas or polars, you end up it's just there's just one good way to do it. I mean, I guess there is more convoluted ways that you can do it, but
that's it. And there's a good point, more general point there about how much like similarity there is. That people often think that their domain is kind of different and very kind of unique and things. That there's a way of laying out your data science project structure, like how you actually have these Python files stored like on your computer in a directory. And there's an approach called cookie cutter, which is saying, actually all data science projects are pretty similar. And so you could just use the same directory structure for every problem. And I've actually followed that approach for 6 years. And I've worked in like 8, 9 different domains over that time. And I've used exactly the same approach for actually structuring the thing for every single project in all these different domains, whether that's pharma, whether that's geospatial, engineering, renewable energy, time series forecasting, all these different things. That actually there's all these really kind of core concepts which just occur over and over again and just in different domains.
So when we spoke briefly about this before, you had mentioned the adoption of sort of data science principles and practices in the financial domain. And it appears that they've kind of adopted it a little bit sooner than engineering. It is definitely becoming more popular now. We're seeing it more frequently, but it's still in its infancy. What do you think about that?
Yeah, well, so it's interesting. It's kind of more than that. I guess because I span different kind of industries, that I've seen this transition from everyone just working in Excel to working more in data science world in 3 or 4 different sectors, whether that was in finance, whether that was in academia, and again in commercial data science. And I saw the transition happen at different points, but in each case, it actually happened in the same way. So when I left finance, there was almost no coding in the kind of consultancy area that I was in. Obviously, in quantitative hedge funds, they were doing full on coding. But then talking to my friends a year or 2 later, when I got excited about coding, and they were at that point, they were like 8, 9 years into their career, starting to become senior, no longer like the kind of engine room doing all the day-to-day analysis. And they were saying, oh, like the new grads coming out of university, that they've actually got a bit of like R, a bit of Python, and that they're now saying like, why are we doing this stuff in Excel? Why can't I do it in Python? It's so much quicker. And it was kind of a threat to to my friends who are now becoming kind of middle level, that they were saying, oh, but then I can't evaluate the work because I don't know Python and I'm too busy and I can't do this. But 10 years later, they eventually had to go back and learn Python because the revolution started from below with the new people coming in saying, hey, I don't want to do this in Excel. I've got these better skills. So when I was in academia, then I was at the point when that transition happened. And again, it was the switch over from using things like MATLAB into Python. The kind of switch away from Excel had already happened there about 20 years earlier, but people had been using MATLAB. But then again, it was the PhD students who were saying, hey, I don't want to use MATLAB and pay for a license. I want to use this like free software that's full of all these open source communities. And the revolution again started at the bottom. And then it was the senior people who had to adapt to it. It wasn't the kind of bosses going out and saying, hey, new strategy, Python, that's the way forward. They were like the last ones kind of to realize that was coming forward. And I think you have to kind of accept that, especially with kind of modern careers, that your career is long, that although you might be in your kind of 30s and you feel like you've got all this domain knowledge now and your skills are set, that it is still possible that suddenly these revolutions come along and that you kind of have to identify them and say, I'm going to be working on this for the next 20, 25 years. I need to actually keep on improving my skills. I can't just say, I'm now middle management, I'm now doing this, that actually you need to keep on developing those skills right the way through. One of the interesting things I saw when working with the engineering consultancy was that I talked to one of the seniors and was saying, hey, why don't you just like train your team in Python and train them in data science? And he gave me what I thought was actually a very honest response. And he said that, one of our problems is that we're not like the highest paying people out there. If we train them, give them lots of data science skills, they'll all leave and they'll go and work for tech companies that have these skills in demand. And that was a really honest answer, because there is this kind of catch-22 sometimes for these employers, that if they look at you and think they give you all these great skills that you want, the chances are, yeah, you might leave. But for me, the lesson was that for the individuals, that you can't always leave it up to your employer to give you the right skills, even if you've identified the right skills and you can say, hey, this would make me better. It may not always be in the employer's interest to do it. So you've got to take the initiative yourself and actually go out there and keep on developing your own skills.
You've raised an excellent point, especially in the consulting realm. If, typically you charge an hourly rate for what it takes to do a task. If you come back to me, if I give you some sort of data analysis task for, assessing the cost of, or assessing the revenue of a power generation facility, and you come back and you say, James, I can do that in 4 minutes, versus me charging a client, 3 weeks of analysis time, like, well, Liam, you just goofed us up. Like, that's a lot of cash gone flushed down the toilet. Of course, my argument to this is, doing stuff more efficiently leaves a lot more time for actually thinking and adding value and quality control and checking stuff and making sure that the deliverables are of a certain standard. So I think it can be short-sighted. Some of the feedback that I've heard throughout the years is like, whoa, let's not get too efficient here. We still need to charge the money. Mm-hmm. So it's interesting, and it kind of ties into what you just said about employers being worried that people might move on to greener pastures or better pay if they're upskilled.
Yeah, and so we've kind of had the experience that in my current job over the last year. So when I came on, my first job was to build out the machine learning part of the system, so we could actually, for all of these sites where we control the batteries, that we can forecast what the energy consumption will be at that site and what the energy generation will be.
And then is that based off historical usage of?
Yeah. So at each site, okay, we have the time series of how much they use and how much they generate. And then we build models for each of those to kind of forecast, okay, so tomorrow we expect that there's going to be high energy usage. We think the weather's not going to be great, so the solar PV generation will be low. So let's charge the battery up overnight and take advantage and make sure that there's energy there, and vice versa. If the weather's going to be good, look, energy usage is low, let's not buy from the grid. Let's wait for the PV to charge it up. Mm-hmm. But so when I first came in, I just built that machine learning part of the system. But then later on, I kind of took over the general software around the battery optimization. And one of the big things I did wasn't actually developing new features. It was building much more visuals into the system so that we could actually see, okay, how is the battery doing? Building dashboards, building things that compare the actual versus the forecasts. How is the battery doing compared to what we expected? And what I find now is when I got new people coming aboard and we're kind of addressing problems, we spend a lot more time just actually looking at the visuals and thinking about the problem, and a lot less time just doing like database queries, writing SQL, trying to figure out where that data set is and how to join it to something else. Yep. You feel the iteration.
Or even like verbally trying to explain your observations without any visuals. Like that's so difficult to do. You're like, okay, you start talking numbers and people just go, they fall asleep. They can't deal with it.
Yeah.
So on that, that's a huge point. And you had mentioned the older generation may not be as familiar with code or wanting to learn a totally new skill. And in engineering, especially, people are very nervous about quality control and being able to check the work. How can I check Liam's calculations if he's written them in Python? That makes no sense to me. However, if you have good visualizations that show your inputs, your outputs, your observations, I think you can span that gap and say, well, you understand what this chart means. Is this what you're expecting? I think that's a big part in bridging the gap between the generations of those that don't want to learn and those that are using code.
Yeah, and so for quality control, that's probably like the main selling point for a lot of consultancies. Again, in my finance consultancy, we were so careful about checking every digit and every bank transfer and things like that. You would like tick them off one by one on the form. And so,
oh my God, that is horrific.
And actually then kind of shocked me in academia because people were just writing this code with just like, okay, out there. And now it's got a lot better. But but what's driven that is really writing tests. So again, for me, I'm doing a lot of engineering type calculations. I might get a certain kind of a certain metric coming in from a battery, and then I need to convert that into, say, energy consumed in kilowatt hours or something like that. So to do that, I write a single function which does that exact transformation, and then that's what you call a test function. And then I have that sits in a. So let's say I have a Python script called sort of transform it into kilowatt hours, transform energy.py. Then alongside that, I have another script called test underscore transform energy.py. So for every Python script, there's another one alongside it, which is called test underscore in the name. And then for every function inside the Python script, there's a function inside the test script called test underscore. And basically, inside that test function, you call the function in your real script, you give it some tiny piece of data, just a single line of data if possible, and then you check the calculation of the output, and you're like, okay, yeah, that's that's kind of like the key calculation that needs to do, and then you run that automatically. So for me, we've built like a full what's called a CI/CD system, and that's a kind of fancy way of saying that before we make any changes to our code in production, it has to automatically run through all these tests, and everything stops if any of these quality control tests fail. And then if they all fail, then it pushes it to the cloud. And then when the automatic jobs kick in the next 10 minutes and the next hour, that actually they're only using the quality controlled stuff. So we're using visualizations and we're using things like that, but there's a major step. Everything possible is put into these test scripts, and then it's fully automatic, and basically nothing can get to the front line without actually passing those quality control tests.
You know, I think this is where our industry is headed. And right now you have, BIM projects where you've got a giant 3D model of, let's call it a bridge. You got a giant 3D model of a bridge, and then you've got the electrical team are going to show all of their conduit routing on the model. You've got the mechanical team. They're going to show all of their routing on the model. The structural guys are showing the reinforcement. The water guys are showing what they need to show. The road guys. So everybody's working together in this giant 3D model. And you can make sure that you don't have conflicts with others. And that's fine in the 3D drawing space. But like you mentioned earlier on, the next layer of abstraction in this fractal progression of design is going to be tying in the actual design calculations and the optimizations of each discipline as you progress. And what you had just mentioned, creating this sort of continuous deployment pipeline of real site data, and then guys back in the design office that are, fixing the problems based on the data that's coming in from site, based on whatever it is. Is it the temperature monitors? Is it the vibration monitor? Is it a flow monitor? All these sensors are going to be giving us continuous data. And as you mentioned, to get stuff done more efficiently, we have to build these pipelines. So I think that's where we're headed. And it's already happening in other sectors.
Yeah, and where I learned that was actually when I started contributing to open source projects. So I think the first one I contributed to was called X-Array. So X-Array is it was started out in climate science, and the idea is that Pandas is great for data that fits in a table. But if you're working in climate science and fluid dynamics, that actually you've got this 3-dimensional ocean you're modeling, and then it's in a 4th dimension of time. And so you're really working with 4-dimensional data generally. And so X-Array was designed to be a version of Pandas, but is ready to work with these multi-dimensional data sets. And so I started getting involved in that and doing some pull requests, and so making some small contributions. And then when you're in those open source projects, everything is about testing. You write one tiny bit of code, and they're like, okay, now we need 4 tests to cover all the kind of ways that can happen. Because that's the whole idea, that you're actually moving forward. Because otherwise you add a bit of code, you break something else, and then you fix that, and then you break something else, and you're kind of more zigzagging. Whereas when you do this test driven approach, that you kind of find a problem, you fix it, you put something in there to make sure that you're not having a regression. It's interesting that a few years ago, one of my friends told me that they were expecting their first child. And he was like, any advice? And I was saying, well, if you want to keep working, once this baby arrives, I highly recommend getting into writing tests, because it's basically taking all the stuff that currently you're keeping in your memory about all these different bits of code in your project fit together, and making the computer just do all the work of remembering. Because I know that you got a new arrival in the house. And I was thinking back to my first sort of 6-9 months after our son arrived. And that how many days when I was just in the office and felt like, total brain fog and felt like Sideshow Bob walking into all those rakes. But those rakes were all the tests, basically, where I changed something, run the test. Oh, no, of course, yeah, that breaks that. Change that. Bump. Oh, yeah, no, of course, that breaks that. But,
Yeah.
that took like 10 seconds to hit each one of those rakes. It's better doing that than like spending 2 days and going, oh, that broke that. Then another 2 days. It's a lot of this. The point of the test driven approach is about velocity, so that some people call it the fail fast approach, because you're writing code all the time, so it doesn't work. And with the test driven approach, you'll find out if things don't work in seconds rather than minutes or hours or days or weeks or whatever. And then once you can do that, then actually that's your progress. That suddenly you're doing something in a few hours, fixing lots of bugs, finding lots of flaws with your initial approach, but you're actually solving that in hours rather than in weeks.
Yeah. Yeah. That's a great point. And it makes me think of, there was another point that you had made before about sort of like the business case of, adopting these principles, and like, how do you pitch it? Because you've got the time and the learning cost of adopting these new tools and kind of changing. You're on a giant, you're on the Titanic, and it takes a lot of effort to change the course of the ship. So you had made a good point about this before, where it's like, yeah, there is a time cost up front, but you can't think about it like that. It's like a major investment in the future.
But for me, it's the way you do code and the kind of testing and stuff like that, that it's so similar to how you would like run an engineering project. And I think like, okay, well, if you're doing an engineering project and you're building a new form of tooling in, like you don't say, okay, right from tomorrow, we're just going to use all the new tooling. That you identify like a small use case where you can start building some experience, learn some lessons, and then kind of expand it from there. So you kind of think of it in the same way of like, okay, well, what is the minimal, what's the first step here? So something to get us going, and that we can evaluate and iterate and kind of decide what the next step is, that you kind of just build it out in stages, that you don't think, because it can seem daunting that you've got all these spreadsheets all over the place, but you've got to like figure out, okay, well, where's the tiniest place we can just start? Who's the person who's really keen, who's really going to put the energy into kind of building their skills and get them, and also importantly, spreading their skills. The person who's happy to kind of share the knowledge, because that's really important in getting coding going in an organization where it's getting off the ground. You have those basically the evangelists. That's what I've seen in academia and in finance, that there's those people who come in and they're just excited and they just kind of like, they're just going to sweep everything ahead of them.
Yeah. 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 I guess, yeah. That makes me think, like, am I an evangelist? Is that what it's come to now? So let's talk about your course for a moment. This is where I first encountered your work, and I was just I was curious about polars. I saw all this information online about how performant it was, but the reality is that in most of my use cases, like here and there, I've run into issues with Pandas where I'm like, this is taking a little bit longer than I would like. But for the most part, it's not usually a performance bottleneck. But as I read more and more about polars, I was curious, and then I came across your course, and I'll put the links and stuff in the description below for anybody that's curious about polars and wants to learn about it. Liam's course is excellent, and it's where I got my start in polars, and I'm using it at the moment actually to go through optimization for an existing hydropower facility, where we're looking at sort of changes in the head water elevations and how that affects power production based on the efficiency curves of the generation units.
Mm.
And so we've got a time series of data going back, I don't know, like 20, 30 years. So many rows of data, and once I got everything set up, once I got the pipeline set up using polars, now I've got intuitive plots and graphs. I can manipulate stuff. I can create all these different scenarios. What if I open the gates 10% more? What if I lower the reservoir elevation by half a meter? And I can immediately see the outputs of all of this stuff, and I can explore many scenarios quickly and easily. And if I try to do that in Excel, I know I could do it, but it would just be every time if you ask me the question of, okay, James, what if you do this? I'd be like, I don't have to do it. It's going to take me ages to give you that answer. But now I can do it just so much faster. So that is just to say, that's how I'm using polars at the moment. And I thought your course was fantastic, concise delivery of everything. And it's only, what is it, 3.5 hours?
Yeah.
And everything you need there to just start using it, hit the ground running.
Yeah. So I kind of will take a step back that, yeah, it's very much like how to use polars. But for me, it's also like I was talking about these key concepts. How do you do group by? How do you do join? How do you work with all these different data sources? For me, it's also like if you're just getting lost in the weeds of data science and you want just like a solid grounding in all the core concepts, for me, it's not just like, okay, how do you use this one library? It's also how do you actually just process data and kind of think and understand, make sure that you know how to do all of these really core things that you'll use on every single project you ever work on. So yeah, so I started using polars. So there's this important question. So I was doing my first workshop on the O'Reilly platform last week. And so one of the things that I was talking about was when I first used polars, the first time I tried it, it was because I was getting a bit tired of pandas, and I had a CSV for a client that would take about a minute to load. So I would normally do like pd.read CSV, so read that CSV with pandas. And then I would like flick over to Twitter and kind of like just waste time for a minute and then wait for it to load. And so I tried it with polars one day. So I did like pl.read CSV, so reading it with polars. And I was starting to go to flick over to Twitter, and I was like, oh, wait, it's already read it. So it was going from like 60 seconds down to like 2 seconds. And that was like, oh, that's actually really cool, because now I'm not getting distracted. I'm in my flow state where I'm like loading the data, and now I'm doing the next thing and doing the next thing, and not just like sitting around waiting for it. When my computer is more than capable of actually doing this quickly. Like with pandas, one of the kind of issues with it has been that a lot of things work on one, like not in parallel, so just one at a time. Whereas polars is built from the ground up to run everything in parallel, so that if you've got these modern computers, they have like all these different CPUs inside them, that actually all of those are being used. The memory's being used. It's all being used efficiently. So this computer that you have, whatever it is, you might not think it's that great. I think you use polars, you'll actually understand how amazing your computer is for doing this stuff. However, okay, that was the first step. I was like, wow, okay, this is so fast. As the kind of 2.5 years I've been kind of involved in polars and using polars have gone on, I've come to realize that actually the speed is great, but it's actually the way it's written, what kind of software engineers would say the API. So that's like how the functions are designed, how you do different operations. And that's really like the real selling point these days, because it's just basically polars was written 10 years after pandas, and just had a chance, like pandas was really the pioneer. And the polars developers had a chance to just be like, okay, there's been pandas and there's been different things in other parts of the software world. Let's learn all the lessons and like make something like that learns all the lessons from the first 10 years. So what I find now is that I'm bringing junior data scientists onto my team, and that the code that I'm reviewing when they're kind of ready to push code into our system, that after having kind of learned polars, that already their code looks really good. Whereas in pandas, it was full of all these like idiosyncrasies, so that you really had to not just like use it, but then you had to learn how to not use it and learn all these little like pro tricks. So again, one thing I was saying in my workshop was that if this was a pandas workshop, I would have been showing you all these like secret little tricks that you have to learn in order to really use it effectively. Whereas in my polars course, there's actually almost zero like secret little tricks. It's all about just like using the library as it was intended to be used, because there's generally just one kind of really good way of doing everything, and just learn those core ideas, and then you just apply them over and over again. So I feel like for anyone, so up until now, I've kind of been saying, well, if you're coming into data science, you probably need to learn pandas, because there's so much legacy pandas code out there. However, if you're coming in fresh, that increasingly I would be saying, actually polars is a great place to start, because it's so clean and it's so much fast and so much more performant, that actually you'll just get like so much benefit out of it. And then you can learn pandas after that, but you won't need to learn all the bad pandas things that you have to do in order to work effectively with it.
Yes, and the reality is too, for anybody out there that's already familiar with pandas, the transition to polars will be very familiar to you, because a lot of the methods and the functions used are almost identical. There's a few differences, but they're very similar.
Yeah, and where they're different, that some I find the polar solution, I was just like, there's things that just even confused me for years in pandas, and then the polar solution was just like doing a group by an aggregation. Like in pandas, it was so confusing how you actually apply a mean to one column and a max to another, and all these different bits and pieces that actually because you do it in almost the same way you do any operation in polars for the same different parts, whether you're doing group by or whether you're just doing a simple max or mean in the whole column, that it kind of works the same in all these different places. So it all fits together much easier.
So I guess I'll just give you my perspective on what I like about the Polars library, and then you can tell me what you think. But like zooming out, I think the big selling points are, like you said, it's extremely performant, extremely fast dealing with large data sets. It also has this lazy frame thing, which I find very interesting, where if you do have a large data set, where in certain instances where I've used it, I've had like the outputs of a big finite element model, a big structural model, which has tons of nodes, tons of outputs for like forces and displacements. So it's a large data set, not large, I guess, in data science realms, but large in structural engineering realms. And polars, you can write your calculations, you can set a bunch of stuff up. And if you use this lazy frame approach, it doesn't run everything every time you try to update your code. You can kind of wait. And it just feels like a more efficient way of working through your problems.
Yeah, exactly. So the kind of idea there is that you've got all your data in CSV and that you want all the data, but you only want the data, say, after 2020. And then maybe there's like 100 different columns in that CSV, but you only need like, and say, an asset ID column and then 10 other columns. And then there's 90 columns you don't care about. That then you kind of write all those steps, like load the CSV, filter out the filter for only the dates after that one, do a group by that column, do all these calculations on those 10 other columns. And then by the time you call collect to actually evaluate that, Polars has a look through that and says, hey, I actually only need 10 of the columns here. So I'm not going to read the entire thing into memory. And then when I'm reading that into memory, I can actually chuck out anything that doesn't meet this condition. And so then you're actually really limiting the amount of data. Whereas before, for me in Pandas, I would have just read the whole thing to memory. Maybe it takes 2 or 3 minutes, and then actually started working on it. And then maybe there's too much for your computer or this kind of stuff. So you really, with almost no effort, you're actually letting like the computer just take over the work and figure out what it needs doing. And one of the exciting bits in Polars in the last few years is that increasingly you've got data sets which are not just stored on your machine, but they might be stored on the cloud. And so with our work, a lot of our data will be stored on AWS. So on Amazon, what's called S3, which is where you basically store your CSVs or your spreadsheets or what in my case, Parquet files there. And that actually Polars can do a lot of that stuff of just picking out the small bit of data that I need and the small bit of rows. And so then I'm not waiting ages for that big file to be transferred across the network. That actually it's just going to that file, picking out the little bits of it that I need and just sending that across. And that's a major, if you can cut out any data being transferred across networks, we've all known networks are a major bottleneck. As soon as you can do that, then after you got like a major advantage in terms of how long things take.
Yeah, and cost too. As you scale things up, especially in your industry, it's like you still have to pay for all of that hosting on Amazon. So the more you can cut out, the more efficient you can make it, the better.
Yeah.
But another thing that you mentioned, which fits into this, is the interruption to flow state when you're trying to solve a problem. So in all types of engineering and code writing as well, I don't know it's a very weird thing because your brain is like, you're in this, like, I don't know what it is. It's like a flow chart of like logic where you just have to think, okay, I need to do this, then I need to do this, then I need to do this. And if you're interrupted for 3 minutes while something is loading, you're gone. You're off looking up some bullshit somewhere, and you're like, what was I? You come back to the problem, and you're like, what was I doing? And you can't find. You're trying to pick up the pieces, and it's like sand, at least for me, anyway. So there's huge value in keeping your head in the game and not being pulled out.
Yeah, because people think, my data isn't 10 gigabytes. It loads in 30 seconds. But if you get 30 seconds down to 3 seconds, which is a common speed up going from Pandas to Polars, that actually you feel it. You feel like your kind of momentum going, and you feel your kind of your effectiveness and productivity go.
Yeah. Cool. There's some other stuff. Oh yeah, I wanted to ask your opinion on, AI tools have become so prevalent. What do you think? I think they're phenomenal for helping you learn in small chunks and giving you context. And I love that you can ask the stupidest, most embarrassing questions in the privacy of your own computer without, Liam asking, where did you come up with such a ridiculous question? What do you think of using AI tools, and do you use them for writing code?
Yeah, I certainly do. And actually today, my Copilot license ran out, and I thought, so if anyone's not familiar, Copilot is this thing you have in Visual Studio Code in the text editor, and it kind of looks at your code and basically like predicts what you might want to write next. And so at its basic level, it's really good, like auto completion. You start writing a line, and it'll just guess what the rest of the line is, and you can just tap and get it, or you can ask questions about your code. In which case, it's not as good as ChatGPT, but it's often okay for simple things. But it was interesting. I was like, okay, well, let's give it a go for a few hours. And I just like, so I after 3 hours, I was like, okay, no, this is no good anymore. I did this 10 years, that writing without Copilot now is actually pretty rubbish. That for one thing, I felt I was just actually having to write so much more. My hands were just getting tired actually of writing. But I was like, I'm just spending all my time writing stuff, and I know what, and something out there knows what I want to write. I know what I want to write. Why can't it just be there? So Copilot, I think I haven't tried Cursor. I think there's a lot of hype around that. That's the next thing I'm going to try. But Copilot itself, like, yeah, definitely, I can't work without something like that. ChatGPT, I thought.
So Liam's talking about an add-on in Visual Studio Code, which is it's a coding environment that I use as well. And it's basically a paid add-on from GitHub that allows sort of autocomplete and auto generation of different code and functions. And it contextually understands what you're trying to do as you write comments and as you write out your code. It's very useful.
Yeah.
Cursor, yeah, I'm familiar with it. That's kind of a fork of VS Code, but I haven't used it myself either.
Yeah, with a different model inside it.
Interesting. Have you tried using Anthropic, the Claude models for code? I think that's the best one.
Yeah, so I signed up actually to ChatGPT's premium last year and paid $20 a month until last month. And then I was like, actually, I'm only using it like in practice like 2-3 times a day. So what I started is using Claude, whatever it's called. And then I just used that for free. And then I ran out today on the 24th of my monthly amount of free things. So I went back to ChatGPT for the rest of the month, and then I'll go back next month. I kind of feel like there's no need to pay for these at the moment. If you're just doing it like this, writing code by yourself, that like I find I don't need the latest and greatest model. That actually, if I want to find out how to write like a simple Python script or a simple Bash script, that actually the basic models are generally fine.
Well, they're fine as long as you know what you're trying to do.
Yeah, as long as yeah, exactly. Yeah, so I feel it's a great time to be learning. Yeah, Python, yeah, because you've got these great things you can just bounce your questions off, and actually, just as long as you're inquisitive, and you can just fire that stuff out there.
It does. I mean, here we have an internal AI tool that we've kind of sandboxed here at where I work, and it's been interesting, like observing how it's been used, because I see a lot of the younger staff are copying and pasting, giant chunks of, be it text or code or data or whatever. And then it's just, you can see they paste in a giant chunk, then they get out a giant chunk, and then they paste in another giant chunk. And it's just this conveyor belt of, they're not even reading it, and they're not even like evaluating what, they're just kind of going back and forth. And I think that's one of the big risks. And I think it's so important when you're using these tools to really try and do bite-sized problems. Like you just go step by step through your code, instead of saying like, design me the Taj Mahal. You have to kind of zoom in, I would say, rather.
Yeah, because I tried it in some areas where kind of I'd know plenty about, like say time series forecasting, and then there I can really see that when it gives you out these big chunks, like you kind of feels like it's been trained on 1,000 bad Medium articles, and you're like, oh yeah, that's like it's really going for the stuff that's kind of been hyped, but like would be considered by professionals and experts not really the right tools. So in time series forecasting, there's a very popular model called Profit, which was released by Facebook and has kind of been disowned by some of the creators, but it just got a lot of hype in social media and is being used a lot more widely than it really should be, because there's other much better forecasting tools out there. And when I went to ChatGPT to say, okay, build me a time series model, it's like, okay, right, profit, here you go. And you're like, oh man, like I've been down that road. I know it's not a happy place that, but then if I hadn't that experience, I'd be like, well, ChatGPT says it's the right thing. That this must be the way to go.
It's interesting because like now everywhere you look online is AI generated content. So are we gonna hit some sort of weird echo chamber where the models are being trained on their own outputs and then the quality of the data just takes a nosedive? It's just interesting because I feel like it's still pretty hard to, like, I know you can read an article and say this is absolutely AI generated, but is it easy to prove that? Like, can they prove something is AI generated?
I think there are statistical properties, but for me, being the more interesting part has been being involved with polars with something that's really new. And so my contributions to polars have been around documentation. So some of the kind of if you look at what's called the doc strings, so if you go onto the website with the API where it tells you how to use a function, there'll be little examples there which explain how it works. And I've written a bunch of those, and I've written numerous pages of the polars user guide. And so for me, it's really interesting.
Which is the polars user guide is excellent as well, by the way. The documentation in general is excellent.
Yeah, very good. A really good community, really good people, kind of really not just keen to develop on the project, but like, yeah, they're doing some really great contributions around the user guide. But yeah, so it's really interesting for me to watch what Copilot, for example, comes out with, or ChatGPT comes out with. If I say, right, do polars, like to do this. And yeah, it's definitely clear that if something's new and developing, that they definitely just can't keep pace. Because at times I wondered, like, should I be writing this course? Like, is writing courses just going to disappear? But actually, in a year and a half, there's no sign that because at times I've been like, oh, well, I can just use ChatGPT to write the course, and then I find out that actually goes a very short way. That actually to build a good course, to make it coherent, put a story together, and actually put all the parts and do the stuff that's really cutting edge, that no kind of model can do that, because they're just not trained on. There's so little material. And then actually for the course, that to understand how most things work, that actually just go to the source code. And they're not at a stage yet where they can just look at the whole Rust source code together and figure out what happens when you do this or that. So yeah, it's clear that when you're at the cutting edge, that they just can't keep up with that kind of thing.
Yeah. Okay. We're running out of time here, Liam. So let's close on sort of your practical advice for engineers out there who are interested in these data science principles. What would your advice be to them?
Well, I think this is you're going to like this advice, because I'll give you some context before I give the advice. That my younger cousin, who's 16, was kind of at a bit of a loss this summer. Had a bit of free time, and he was interested in learning to code Python. And my advice was like, okay, well, don't just like look for a random online Python course. Chances are a lot of those actually are aimed at web developers and will kind of try and teach you a bunch of concepts you don't need. What you want is something that teaches you Python, but in the context and the domain that interests you. And so I know that that's like right up your street, right? Because you write a bunch of Python things for engineers. And so in his case, when I went online and Googled and found like a website which teaches Python, but using football statistics, because he loves soccer, loves Gaelic football, things like this. And then he went and did that, and he just really enjoyed it, because straight away you're looking at data you're interested in, you're making plots, you're getting into it. So I think the first thing is find some resources, and James has got a bunch of them, that just really are geared towards that your domain and will have problems that you're interested in and kind of challenges that you're interested in. And you'll find it a lot more engaging, and you'll get to that kind of like takeoff point where suddenly your own momentum takes over, and you're able to work on your own problems and start learning like the whole process yourself.
Yeah, that's great advice. And it felt, for me anyway, the beginning was difficult because it's so abstract and you're kind of like, what? Like your brain is just trying to like understand. It's a totally different way of doing stuff through code. And once I got through the first, say, 6 months, then I was able to walk. And once you're able to walk, you can go wherever you want to go. Mm-hmm. But the act of learning to walk was tough.
Yeah.
That was my story. Like, what was it like for you when you started coding? Like,
I was lucky because I had definitely. I started off with a course in a master's, which is 3 months of like, okay, learn how to MATLAB. So I was lucky in that sense that there was actually a guided program. But it is amazing with software, because there's so many like jobs that you kind of like when I was a financial consultant, after a couple of years, you felt like the learning curve was really shallowing off. Whereas now I feel like I've been writing code for 12 years and I still feel like I'm learning new stuff all the time. And it's really, there's just like, I don't think the learning curve will ever really stop. So you just got to like get into the point where it's not actually the point where you just do like a couple of weeks and you're there. That it's actually this beautiful kind of like process where you're just continuing learning cool new stuff that you didn't know that you could do until the day before.
I feel it's almost like an analogy that I explained recently was like, it's almost like it's a type of Lego where once you know how the Lego works, you can build whatever you want, but it's kind of difficult to learn how the Lego works at the beginning, you know?
Yeah. I'm guessing your house is full of Lego like mine.
Yes, it is. It is, unfortunately, for the soles of my feet. Okay, Liam, thanks a million for the chat. Really appreciate it.
Yeah,
And I really hope that everybody takes a look at your fantastic course on polars in Udemy. I know I'll be going back to it many times to figure stuff out. And
by the way,
hopefully we talk.
It's kept up to date, so you're free. If you sign up for the course, you're free to download, because every week or two I'm keeping on updating it, so it always stays fresh. So
awesome. Okay, thanks a million, Liam, and we'll be talking to you in the future.
Great. Thanks, James. Good talking to you. Bye.